Hi, my name is Lawrence Chen. I'm a senior from Cupertino, California, and this is my Polygence project on post-combustion capture and direct air capture of carbon dioxide. Now, it's no secret that global warming and mitigating greenhouse gas emissions has been an issue of incredible urgency in recent years, especially carbon dioxide, which accounts for 80% of our total greenhouse gas emissions. Now, in response to this crisis, the International Energy Agency listed carbon capture as an integral component to their net zero by 2050 roadmap. And I was very intrigued by carbon capture because graphics like this one from Forbes just make it seem so intuitive and just enticing. And I really wanted to look into the process for myself. So there are two promising carbon capture methods gaining traction right now. The first of which is post-combustion capture, in which carbon dioxide is captured directly from a point source after combustion. So you can see here in this diagram, we start with a flue gas, which is basically all the nasty stuff that's released from like a coal-fired power plant. It's sent to an absorber where CO2 is then absorbed and then undergoes a purification process to output very high purity CO2, which can be used for commercial use. The next major method is direct air capture, in which carbon dioxide is captured directly out of the ambient atmosphere. And there's many emerging businesses like Climeworks building several direct air capture facilities, such as the one seen here all over the world. So it's gaining a lot of traction. What I wanted to do was assess the state of carbon capture based on existing literature, and I wanted to compile and compare all materials in one place so that future researchers can use it and be informed of the state of the fields as of right now as well. I also wanted to use my results to make inferences about the field of carbon capture research, as well as the role of carbon capture technology in the future as a whole. I used the Department of Energy's Carbon Dioxide Capture Handbook to classify the materials and help me start searching. And I also wanted to report commonly reported statistics like capture efficiency and operating temperature. And then finally, I wanted to assess every single material on the technology readiness level scale, which is a scale from 1 to 9 that assesses whether technology is in the lab research stage to early development, all the way to widespread deployment. So I was able to write a research paper in which I analyzed 14 different carbon capture materials in total, creating thorough written descriptions of each. So here are my results for post-combustion capture, and instead of describing each material, I'll just group them into major categories. First of which being solvent-based capture. So in solvent-based capture, CO2 is absorbed at the interface between CO2 gas and a liquid solvent. Solvents are mature and have been widely commercialized for years, such as monoethylenol-amine, which has been used for this purpose for a very long time. And solvent-based capture tends to face a viscosity trade-off, where less viscous solvents, such as aqueous solvents, have very high diffusion efficiency, but also very high thermal requirements, since aqueous solvents contain water by definition, and you need to heat them up to a high temperature in order to evaporate the water away when you're regenerating the solvent for repeated use. Conversely, more viscous solvents have a slower rate of diffusion, but also lower thermal requirements because you don't have to evaporate that water. And generally, solvent-based capture fares worse than solids for regeneration. Next is physical adsorption. And just to clarify, adsorption with a D is when carbon dioxide is attracted to the surface of the material instead of getting absorbed into the material. So in physical adsorption, CO2 is attracted to pore walls by weak dipole forces. And the trade-off here is that large materials with large pore size are able to maximize the rate of diffusion, while materials with a small pore size are able to maximize the total surface area and maximum carbon capture capacity. Now, physical adsorption has fairly low energy requirements because there's no water involved, and when you're collecting the captured carbon after the process is done, undoing those weak dipole forces requires quite a low amount of energy. One thing I noticed in my research is that Nanomaterials can be very expensive to produce, such as carbon nanotubes and graphene, but the results look very, very promising. Next is chemical adsorption, in which CO2 is instead absorbed by the formation of strong covalent bonds. And because of these strong bonds, chemical adsorbents tend to have a very high CO2 affinity, but conversely, they have high energy requirements because breaking those bonds requires a lot of energy as well. And one other issue with chemical adsorption is that potential attractions can form with non-target molecules in the flue gas stream. The next is membrane-based capture, in which a gas stream is just passed through a permeable membrane and CO2 is selectively captured. And this is possible when different gases in the flue stream have different relative permeabilities. So you can selectively collect all of the CO2 in one place in the membrane. This process is very simple and energy efficient and doesn't really require any water at all. However, it requires pretty substantial initial costs to set up just because of the sheer amount of infrastructure that is necessary to set up these extensive membrane systems. Membrane-based capture is also quite sensitive to trace impurities in the flue stream. Now moving on to direct air capture, which I'll just cover in this one slide. So when you capture carbon dioxide directly out of the existing atmosphere, that allows for theoretical net negative emissions. And compared to other ways of sequestering carbon, such as planting trees, because you're building dedicated direct air capture plants, direct air capture has the benefit of being able to be deployed anywhere, not just arable land. However, the requirement of having to construct new plants can not only be very expensive, but also environmentally harmful, since just due to the sheer amount of resources that are necessary to construct these large facilities. Direct air capture is also an incredibly inefficient process due to there being such a low atmospheric concentration of CO2 at only 400 parts per million. In addition to expensive construction costs, direct air capture is also quite expensive to operate because of that low efficiency. So much air has to be circulated through the system 24/7 in order to capture a meaningful amount of carbon, and that requires a lot of energy. As for materials, solvent and solid sorbent systems are both used. However, solid sorbent is much more preferable in terms of water consumption, as solid sorbent systems consume roughly 1.6 metric tons of water per metric ton of CO2 captured versus up to 7 for solvent systems. In my research paper, I compiled two tables, the first of which being a qualitative table summarizing the advantages and disadvantages of each material. Here's just one cell from my table. And then next, I made a data table compiling the carbon capture efficiency, the flue concentration of CO2 used in the study, the technology readiness level I determined, and the optimal operating temperature of every single one of my materials. But what were my conclusions? So here are my major takeaways. I found that no post-combustion carbon capture method is unanimously superior, but some of the more novel non-aqueous materials, such as graphene and aluminum fumarate tetraethylene pentamine, are very promising. And this suggests that it's very much worth funding the technologies that are still in the research development stage, since I found that the options with the lowest technology readiness levels are actually the most appealing with the most benefits. And I agree with experts that direct air capture is just too expensive and inefficient to justify in the short term. Maybe a few decades down the line when the technology is more mature, but not right now. As for major limitations in my research, I noticed a lot of inconsistency and omissions in the field when reporting lurking variables, one of which being the partial pressure of CO2 used in the flue stream whenever conducting an experiment for a material. That was often left out of the research paper reporting the experimental data. And I also found a lot of review papers similar to mine that directly compared two materials without reporting the concentration of CO2 in the flue gas used in each study. And when I investigated the sources for some of these papers, I found that the CO2 concentration used was actually completely different in those two studies, but that figure was not reported, which could lead to the potential confounding of data and misleading information. So in the discussion of my research paper, I really wanted to address this major lack of consistent reporting I noticed in the field. Another limitation I noticed is that the costs and energy expenditure variables were usually unobtainable. And I also noticed a lack of documentation on the longevity of many of these technologies, um, such as a life cycle analysis, just because many of them are so new. Finally, what do I believe the role of carbon capture is? I think it cannot be used to justify the continued future growth of the fossil fuel industry. Um, and the International Energy Agency's simulated plan that I referenced earlier actually only uses carbon capture to decarbonize a select few industries, being mainly the cement, steel, and chemical industries. And this makes sense because these three industries require so much on combustion for the manufacturing process that um, the option that makes the most sense is simply continuing to rely on combustion and then using post-combustion carbon capture to um, mitigate the emissions from those sources. However, for all other applications, transitioning to renewables as an energy source should take precedence. And it's also worth being aware of that carbon capture can be used for greenwashing. It can skew climate simulation data, but it can also actually be environmentally detrimental in certain use cases because of something known as enhanced oil recovery. And this is where pure CO2 is actually used to extract more oil out of the ground. And what that does is that a common practice has emerged in which fossil fuel companies are major carbon capture ventures in order to appear sustainably conscious to the public, when in actuality, they're using that captured carbon to only fund their own business interests and extract more oil, which is just something that I believe the public should be aware of and cautious of when reading about carbon capture in the headlines. Yes, I really hope all of you learned something, and thank you so much for listening.